The goal of this video is to introduce the viewer to the cosine rule. So we've got two videos in succession. This is video 1, so you could call this the cosine rule number 1. The cosine rule, like you saw previously with the sine rule, can be used on any triangle. So it does not have to be right angled triangles. Okay, so any triangle. And not restricted to right angled triangles. Alright, so you might remember that regular sine, cos and tan ratios, you have to have a right angled triangle. Also, Pythagoras Theorem was restricted to right angled triangles, but the cosine rule is not for any triangle. So for triangle ABC below here, it would work if we had enough information. That's not a right angled triangle. Where does the cosine rule come from? The proof or the derivation of it is quite complicated, so it won't be shown in this video. Just to cut it down to basics, but it's a little bit like what we did with the sine rule, where we saw where that came from, in that we get a non-right angled triangle and put a extra internal line down there and create two right angled triangles. But the actual work involved is a bit more complicated, so we're going to skip that for this video. Now you have a job to do before you progress further on into this video. You need to see if you're ready. So here's some accountability questions to see if you are ready. Have you absorbed the previous work enough? Have you mastered it so that you can learn the content of this video in the next one? So I'm going to put 3 questions up on the screen, and I want you, as you work through them, to pause the video, and you need to write your full solution in your Cornell notes. So when I see your Cornell notes, they will have full solutions to these 3 questions. So the first question is, with the right angled triangle, we have a side A, which we don't know. There's the right angle. The hypotenuse is 55. This side is 33. I want you to find the length of A showing working. Question 2, I want you to find 2 answers for theta, or 2 solutions for theta, if cos theta equals negative 0.766, it's a 6, sorry, 04. So in other words, what is the value of theta if cos theta equals negative 0.76604? And there are 2 answers. There's a part B to question 2 as well. Which answer from A, from above, which answer out of those 2 that you provided is possible if theta is in a triangle? So you'll have 2 answers for part A and only one of those 2 answers for part B. So 2 answers for part A, 1 answer for part B. The last question, in the right angle triangle shown in question 3, I want you to find H and show full working. It's a regular right angled triangle. Well, it's a right angled triangle. I won't say regular. Find side length H, show working. Now that you've finished the quiz, here is the cosine rule. The cosine rule is, if we have a non-right angled triangle, or any triangle in fact, because it does work with it definitely does work for the right angled triangle, but because it's more complicated, you might as well just stick with regular sine, cos and tan ratios. Usually we use this for a non-right angled triangle. So for some triangle with those vertices or angles and those sides marked, as you can see, these are the 3 forms of the cosine rule. So a squared equals b squared, a squared equals b squared plus c squared minus 2 times bc times cos of a. Remember, lowercase are sides, uppercase are angles, like you've seen previously. The other form which will work is b squared equals a squared plus c squared minus 2ac cos b, and lastly c squared equals a squared plus b squared minus 2ab cos c. Now if that seems a little bit daunting, there are patterns to help you remember it. Alright, if you are chasing side A, trying to find side A, you would have a squared as the subject. You'd also have the angle A at the end. See that pattern? Also, if you have A at each end, you will have b squared plus c squared there. Now, does that remind you, the first part of that formula, does that remind you of something? Have a think. Does it remind you of Pythagoras Theorem? You've seen Pythagoras Theorem for a right angle triangle can look like a squared equals b squared plus c squared. It's got some extra stuff on the end, of course. So we've seen that if we've got a squared and a on each end, you've got b and c in the middle, and then you've got b and c there, but it's 2bc, 2 times bc. Be careful there, that is a subtraction, so do take care with the calculations. The same idea follows through in the other forms. You'll only choose one of these. Alright, you don't use all three in a question, you just choose one of them. Whichever one is relevant to the question you're doing, whichever one will help you solve the problem you're trying to solve. If you're trying to solve for b, you'll have this form, and see how the b's are on the ends there, and we have the other letters in the middle. And likewise with c squared, if you're looking for c, you'll use that form, and it has the other sides in the middle. Make sure that is copied, it's very important. When we did the sine rule, we saw that it was useful for solving problems with certain information given. The cosine rule too, it works best with different information given than the sine rule. So the cosine rule is used when you are given a triangle with two sides that you know the length of and the included angle. Now what that means, you might remember that, for example, if we were given this side length, you knew the length b, and we were also given this side length, we knew the length c, the included angle between this and this is this angle here. That's the included angle. Okay, it can't be one of the others, so see how that angle falls between the arms of the two sides. The other situation where you would use the cosine rule is where you're given no angles but you're given all three sides. The next video we will look at two examples to show how all this works.